Hello, welcome back. This is Dr. Oz from Western Kentucky University. Today we're going to go over a few exercises that we're going to practice using a trigonometric identity together with u substitution or log rule. So our integrals, in the first one you have cosine t divided by 1 plus sine t. In the second one you have secant x tangent x divided by secant x minus 1. So let me just remind you about the integrals of 6 basic trig functions. Well, we have seen sine and cosine in previous chapters that sine has the antiderivative minus cosine u, and then cosine u has the antiderivative sine u. But we have also tan, cotan, and secant and cosecant. So these are somehow related to ln type integrals because the log rule applies for each of those last 4 integrals. Okay, for example, tan is sine over cosine, and that's where we call the cosine to be u, so that after the u substitution, you rely on to the log rule to integrate, and that turns out to be minus ln cosine u plus c. And you can do all like others by the same u substitution and log rule applied all the way. So today for the first part, for the first integral, so we're going to sort of like rely on to a u substitution directly. Since we have cosine divided by 1 plus sine t in the first exercise, and we know how the bottom and top are sort of like related to each other, because if you call the bottom to be u to start with, you know that du is going to contain the top times dt, because here du is u prime dt, and u prime is the derivative of this whole chunk 1 plus sine t, but 1 has the derivative 0, and sine has the derivative cosine. So then this would be cosine t dt. What I'm trying to say here is that if you use a u substitution where u is 1 plus sine t, you can convert this integral here into the u version of that, which is much easier to work with, because cosine t dt, I'm going to call it du, and I have the whole bottom called to be u. And now we can just use the log rule for integration, which is essentially stating that this is equal to ln the absolute value of u plus c. Okay, since u is 1 plus sine t, I can go ahead and write that this is equal to ln of 1 plus sine t plus c. Well, the observation here is that the derivative of the bottom has cosine t dt in it, so it was sort of like an easy change of variable and then redefining that integral with the new variable u. You can also use algebra to find or to evaluate this integral. This was kind of like a function that we have seen earlier, cosine t divided by 1 plus sine t. You can always multiply the bottom of the integrand by the conjugate of that. In fact, let me just do it quickly here. So you have cosine t 1 plus sine t. Why don't we multiply and divide by the conjugate of the bottom, which is minus sine t, right? So that the top becomes cosine t 1 minus sine t, and then this is all divided by 1 minus sine squared of t. So if you use just algebra here, this is probably what you get, but you have the Pythagorean theorem to replace this by this is equal to cosine squared of t. Okay, so that allows me to cancel the cosines here. So let me just write it here. So 1 minus sine t over cosine t. So as you see that, instead of cosine t divided by 1 plus sine t, I can use 1 minus sine t divided by cosine t after using the trig identity, which is sine squared t plus cosine squared t equals 1, so which is used here, right? So now I can split this into 2 parts. I can write this as like 1 over cosine t minus sine t over cosine t. Okay, 1 over cosine t is the reciprocal of secant, and sine over cosine is just tangent of t. And then see, like you know how to integrate the secant function, which because there's a rule for that, as well as a tangent function. So this rule and this rule applies here because you replace the integrand cosine t divided by 1 plus sine t by secant t minus tangent t, which is not obvious to see in the beginning because we used algebra and a trigonometric identity. But essentially, you can just write down the integral in terms of the integral of secant minus tan. The resulting function after the integration may look like different, but essentially after enough simplifications, both integrals are going to be equal, so it should be like ln of 1 plus sine t in the absolute value. So here what I wanted to show to you is that you can use a u substitution as a detour of the solution, and if you sort of like can't see that u substitution is applicable here, your last resort is to use the algebra, but that requires too many steps to get to the final version of the function for which you can use those formulas. All right, for the second integral, we have secant x tan x, and in the bottom you have secant x minus 1. If you remember the differentiation formula card, that we know that secant function has the derivative secant x tangent x, so that sort of like allows me to call the bottom, the whole bottom, to be u, so that when you take the derivative of it, secant x tangent x dx is going to pop here. So this integral is going to be very simple to integrate. So what I'm trying to say here is that call the whole bottom to be u to start with. And again, I'm not trying to use any algebra here because the algebra is cool, but it may take longer to get to the final version of the integral, which is sort of like easier to integrate by using the integration rules. So I'm going to do du equals u prime dx. All right, so u prime is secant x tan x. How do I know that? Because secant x is one of the basic functions, and we talked about the derivative of that in the differentiation formula card, and it has a derivative secant tan. Again, the good news is that the top of this integral, including dx, is now exactly equal to du, right? And the whole bottom is just u. So now this is a kind of integral that we know how to integrate because of the log rule that we covered in this section, right? If you have du over u type integral, so then you can write that this is equal to ln of the absolute value of u plus c. And you can go ahead and replace u by secant x minus 1. Let me just write it here. So this is going to be equal to ln of secant x minus 1 plus c. All right, so in this example, we utilized the u substitution because soon after I saw the bottom to be secant x minus 1 and the top to be secant x tangent x, it flashes that the bottom is u, as you see, and du has secant x tangent x. By the way, if we did not have any secant x tangent x, or if we didn't have secant or tangent at the top, it would be extremely difficult to use the u substitution because du is secant tan, so you can't miss one of those functions in the integrand. If you don't have those functions, then it could be slightly harder to rewrite this integral in terms of the u version of that. In this case, it's just du over u. Otherwise, it could be way much harder. All right, this ends the video. Thanks for watching. I'll see you in another video. Bye.